Okay, good morning. Let's try that again. Good morning. Good, much better. Today we're going to look at two sections at the same time. They both deal with applications of double integrals, so they're closely related. And this will be the last lesson we spend on doing double integrals. Pretty soon we're going to be moving on to triple integrals, but same idea. You can do 2, you can do 3. Now we've seen stuff like that. Okay, so the first thing we're going to do here is, if you imagine, this is a problem dealing with finding the mass of what's called a lamina. And a lamina is just a fancy name for a thin plate. Okay, so imagine you have a very thin plate that's got some arbitrary shape. So as usual, let's say the shape is defined by something like that, right? Some kind of shape here defined by the region D. And we would like to find the mass of that plate. If this is an elementary shape like a triangle or something, that's not hard to do. But any kind of arbitrary shape, that's going to be a little bit more difficult. And further, let's assume that we have an areal mass density. And that some function rho, this is Greek letter rho, lowercase rho, looks like a p, but it's not a p, and it's a function of x and y. In other words, every single point can potentially have a different mass density. Okay? And that's the case with a very general shape. And we'd like to find the mass of that little plate here. So think about how this is done. Imagine if you take a very tiny little patch of that lamina out. So this thing is going to have a width of delta x and a height of delta y. And of course, the area is delta x, delta y equal to delta A, right? And so the mass of that tiny little patch here is going to be roughly equal to whatever the area is times the mass density at nearby that point. So it's roughly rho xy times delta A. Okay? So that's the mass of that tiny little thing. And now we do our calculus trick. We shrink delta A so that delta A becomes dA. So a mass of tiny little patch on this little lamina here is going to be rho of xy times dA, right? That's one tiny patch. So what do you do when you want to find the entire plate? You accumulate all of these little patches. And how do we do that? Integrate, yep. Mass of entire lamina Therefore, it's going to be m equal to a double integral over that region. We know how to do that, times the areal density dA. Okay, physically is what this is doing is we found the mass of one little patch. The double integral accumulates all of these infinitely many little patches. And once you accumulate all of them, that'll give you the mass of the entire plate. Okay, so that's not a difficult concept. Let's continue dealing with a little bit more physics of this plate. You might remember we calculated the moment about the x and y axes when you took 162 or 166. I'm going to revisit that problem a little bit. So we got this little region D again. And once again, let's imagine we're dealing with a little bit of a tiny little patch right here. And in this context, the moment of an object from an axis is equal to the distance from the axis multiplied by the mass of object. Okay, so this tiny little patch in green here has a distance from the y-axis given by x, right? X is where that patch is, and x is also the distance from the y-axis. So the moment due to that little patch right here is the mass, well, actually the distance from the y-axis, which is x, times the mass, rho xy dA. That's that one patch. And now I want to account for the entire plate. We do another double integration. So the moment, capital M, subscript y means the moment about the y-axis. In other words, this thing's going to start tilting around the y-axis if you let it go, right? And moment measures the rotation about the y-axis. And once again, what do? You take the moment due to one patch, then you integrate over the entire region. So double integral over d, x, rho xy dA. So that's the moment about the y-axis. And similarly, the moment about the x-axis, same idea. Distance from the axis times the mass of the object. You do the same thing here, except this time the distance from the x-axis is y, right? So this guy right here, the distance is y. So for the moment about the x-axis, capital M subscript x, double integral, and instead of x over here, we put y. And normally you calculate a moment so that you could find the center of mass of that object. And that's the very last thing here. We're going to write down the center of mass. often called the centroid. And very often you'll see the location denoted by x with a line over that. That's called x bar and y bar. That's the location of the centroid. And the center of mass is the location of a particle that has the same mass as the lamina. And also has the same moments. Okay, imagine if you take this entire plate, collapse that into one point, one single point with the same mass as that entire plate. Where are you going to put it so that a single point would produce exactly the same two moments? So that's how we find the center of mass. Okay, now instead of that plate, imagine this thing's collapsed into one point right here. Right? Distance from the x-axis is y bar, and distance from the y-axis is x bar. The moment of that point about the y-axis is the distance from the y-axis times the mass of that one point. And remember, now we want the same moment and the same mass as the lamina. It's the same thing, but collapsed into one point. So if you take the equation my from the previous page, replace that here, and you take the same mass from the two pages ago, okay, these things we derived on the last page and the previous page. This will tell you where the center of mass, the x component of the center of mass. So x bar would be 1 over m, that's this guy right here, times the double integral x rho xy dA and similarly for the y component of the center of mass, exactly the same idea, except we use the distance measured from the x-axis this time, which is y bar. You would get 1 over m double integral over d y rho xy dA. And again, m is just the mass of the plate. All right, so this is how we find the center of mass. And if you look at these equations, they kind of match up, right? There's an x over here, there's an x over here, y here, and a y here. So if you know one of these equations, you know the other one. But if you forget the equations, just remember that what do? We just calculated the moment of one point. And that's going to have the same moment and mass as the lamina. Okay, let's try this on something. Let's have a lamina that occupies the region bounded by y is equal to x and y is equal to x squared. The density of this plate is proportional to the distance from the y-axis. Okay, the shape is defined by a region bounded by two curves, pretty simple curves. And the density of this thing is proportional to the distance from the y-axis. In other words, the farther you're away from the y-axis, the more dense it is. The mass is concentrated away from the y-axis. Okay, so let's check out what we're dealing with. Y is equal to x. That's just a straight line right here. Y is equal to x squared is a parabola. And these two things only bound the region in the first quadrant. They don't ever intersect again, so they don't bound any more region anywhere else. Where do they intersect? This should be very easy to figure out just by inspection. 1, 1, yeah? Okay, so that's the region we're dealing with. This looks like it's set up for either a type 1 or type 2. It doesn't really matter. Both of those are easily done with. So let's just go with a type 1. Okay? Let's let x be bounded by constants and y bounded by top and the bottom. Top is x. The bottom is x squared. You could also do a type 2. It's not difficult. It's the same, pretty much the same thing. Okay, so mathematically, how do we express this sentence right here? Proportional to the distance from the y-axis. Yeah. K over y? Well, let's see. Here's some point, right? What's the distance from the y-axis? X, right? So something proportional to that. And you're right, we need a constant of proportionality. That's what a k comes in. So it's k times x, right? K is just some constant. Constant of proportionality. So notice that density will get bigger the bigger x is, the farther you're away from the y-axis. When you're really, really close to the y-axis, it's not as dense as when you're farther away. And you would do this for various reasons. Maybe you want to have more dense material out here because maybe it's slicing something, maybe potentially, or because it's rotating so that you want the part that's being subjected to the greater centripetal force to be stronger. Possibly. There are many reasons why you would want to build stuff like that. Okay, anyway, let's calculate the mass. Double integral, density, small patch of lamina, dA. All right, type 1. So remember, the one that's bounded by constants has to go last. X has to go last. Y must go first. Rho kx. dA, we're going to do dy first. So dy dx. And this will be very easy to integrate. We get kx times y. Y is x minus x squared. dx 0, 1. Let's take the k outside. X squared minus x cubed. And we can all do this. This is very easy. 1 over 12k. Okay, without knowing k, we can't do anything else. It's whatever the constant of proportionality is times 1 over 12. And that's the mass of that lamina. Okay, now let's calculate the center of mass. Let's start with a moment about the y-axis. Okay, the moment about the y-axis is a double integral over the distance from the y-axis, which is x, times the mass of some tiny little element, dA, rho dA. And we pretty much just duplicate what we just did. Same region D, right? So same integration limits. X times kx. dA is dy dx. And this is a very easy integration, so I'm going to skip the steps. You should get 1 over 20k. And similarly, for the moment about the x-axis, we take the distance from the x-axis. So you're moving up and down. That's the y times the mass. Density times a small patch of area. Again, same integration. Limits y times kx times dy dx. So this time you integrate y first, y squared over 2 and all that stuff. Again, a very easy integration to do. And we should get 1 over 24k. Okay, finally, the centroid, x bar is my over mass, right? 1 over 20k over the mass, which is 1 over 12k. Notice the k's disappear. Because the centroid is more of a shape property. So exactly what k is, it gets factored out. It depends more on the shape of the object. how it's spread out around the center of the mass. So it's not really dependent on k. Even though the mass and the moments depend on k, the centroid itself, again, it being a shape property, doesn't depend on k. For white bar, it's 1 over 24 k, that's mx, over the mass, and that gives you 1 over 2. Again, no k, right? So this means that the center of mass of this little half-moon shaped thing is going to be at x is equal to 0.6 right here, and y is equal to 1/2. So somewhere over here. Notice that it's not a geometric center of that shape. And the reason is because it's more dense away from the y-axis. There's more mass on the outer half than the inner half. So if you were to balance this object, you would put your finger underneath the center of mass to balance that. And it wouldn't be at the center because of the non-constant density. Okay, questions? Nope? Good. Okay, the next thing we're going to use double integrals to do is to find the surface area. Okay, imagine you got some kind of surface. I'm going to draw a part of a sphere here. And it's projected down onto the xy plane. And that's our region D. So we know how to find the volume of a solid underneath this cap above D, right? You just integrate over D, whatever Z is. And now we would like to find out the surface area. So we're going to use very, very similar trick to how we did the mass and the centroid. We're going to focus on one point somewhere near on the surface. Let's say right here, just some random point. And we're going to look at the tangent plane right near that point. I'll blow this up over here. Okay, so this tangent plane over here is, I'll draw that bigger. This guy right here. And this is the point xy. And near this point here, remember the surface right below it, that's part of the surface right here. Remember, if we stay really close to that point, then that part of the surface will look very much like the tangent plane. So what that means is that the surface area near that point xy is going to be roughly equal to the area of the tangent plane near xy. Does that make sense? A tiny little region near this point, that surface is about the same as the tangent plane. So if I could find the tangent plane area here, near that point, that's going to be roughly equal to the surface area, that little portion of the surface area right below the tangent plane. And if I keep shrinking the tangent plane here, the approximation gets better, and then I integrate over the whole thing. So that's the idea here. So how do you find the area of a plane like that? Remember how to find the area? It has something to do with vectors. What's that? Cross product. Very good. Yep. Let's imagine that this edge here is the vector A. And let's imagine this edge right here is defined by the vector B. And we know that the area is equal to the magnitude of A cross B. Right? Remember that? And you thought you wouldn't use that formula ever again, right? It's back, and we need it. It's a very important piece of the puzzle right here. Okay, now the question is, what are A and B for that tangent plane? Let me sketch that picture again, and we'll figure out what they are. Here's my surface. It looked better last time, but it's the same thing. And I'm exaggerating the tangent plane here. And here's the point that we're going to find out the vectors A and B from. Okay? So this point, it represents that point, and A, this vector A is this edge right here. This vector B is right here. So we've done something very similar to this before. What we're going to do here is to make a cut at a constant y. And that's using trace again. Y is equal to some constant. And you thought you were done with traces. No, we're not done with traces. Okay, now I'm going to look at this red curve here on the xz plane. And that red curve is roughly like that, right? And that point is right here. That's the point xy. And this dotted line is the tangent plane from the side, right? The plane from the side looks like a line. What is the slope of that dotted line, that blue line? We've done this before. Say that again. The derivative, what kind of derivative? Partial derivative of what with respect to what? Good, very good. Okay, so that's the partial derivative of z with respect to x. So this green vector that lives on that tangent line right there, that's our vector A. Let me blow up the picture here. We'll find out what A is equal to. So that's our vector A. So looking at this edge now, that vector A looks like this from the side. And the vector A is made up of two vectors. It's a vector going in the x direction. That's delta x I. And then the vector going down or up, doesn't matter. And what that vector is, it is partial of z with respect to x times delta x. And it's going in the z direction, up and down, so it's in the k direction. And this is true because we know the slope. Slope is rise over run. If you take this divided by that, that gives you the slope. So we work from the slope backwards by inserting a vector going in the I direction and then the k direction. And the change in x, that's delta x. So what this tells us is that A is equal to delta xi plus partial z, partial x, delta x, k. Now we figure out A, we figure out B exactly the same way. We take a trace, now this time for a constant x, and all of these repeat, except this will be partial z, partial y, and this will be j instead of delta yj instead of delta xi. So that part we can we'll skip the details there. Similarly, the vector B becomes delta yj plus partial z, partial y, delta yk. Okay, now we can calculate the area of that small tangent plane. And that's going to represent the area of the true surface right below the tangent plane. And then we integrate over the whole thing. If you do A cross B, you get partial z, partial x, I minus partial z, partial y, j plus k times delta x, delta y. And by the way, this is dA, delta A. Finding the magnitude of this square plus that square plus that squared, right? Sum of the squares of that. That's a vector. Finding the magnitude is the square root of the sum of the squares. So this would be partial z, partial x squared plus partial z, partial y squared plus 1. All of that under root times delta A. So the important thing here is that that gives you the area of one tiny patch on that surface. Even though this is true, actually in reality the area of the tangent plane, we already know that if it's small enough, that will be about the same as the true surface. And if we shrink this, oops, that's an A, sorry, not X. So now we do our calculus thing. We shrink delta A to dA. And then integrate over the region D. Remember, region D is the shadow of that surface on xy plane. We integrate over that. So that's going to give you surface area of the entire surface. All right, SA for surface area. Double integral over D of this stuff right here. dA. Okay, so that's where that formula came from. All we did is we found a small patch of a tangent plane, found the area of that, and say that they're the same thing once it shrinks to dA, and then integrate over the entire region D. All we're doing here is accumulating a tiny patch all over the place, over the entire thing. And this formula looks a lot like the arc length formula, if you remember. Arc length is a single integral and without that thing here. Looks very much like that. Okay, now let's try this on something. It's a formula, not hard to use, but we'll try it on something. Let's find the surface area of a plane 2x plus 13y plus z is equal to 26. In the first octant. Okay, you got to remember that these planes are infinite planes. So if I just stop the problem right there, then the answer is infinity. The surface area of an infinite plane is infinity. But we're looking for a patch of that trapped in the first octant. And the first octant is where all three variables are positive. It's the three-dimensional equivalent of the quadrant. Okay, so let's figure out what this looks like in the first octant. It extends forever, but only the patch in the first octant is what we want to know. To sketch this is pretty simple. If you let y and z be 0, then 2x is equal to 26. That tells you that when y and z are 0, you're on the xz plane now. X is 13. So that's the intersect. The x-intersect is 13. You make two of these 0, it'll tell you the intersect on that axis. If you repeat that, if you let x and z be 0, then you're looking at the yz plane now. And 13y is 26. That tells you that it's going to cut through y-axis at y is equal to 2. And similarly, if you let x and y be 0, it's going to cut through the z-axis at 26. So that's how you figure out how to sketch this kind of shape. So what we get here, we're going to get a triangular shape. It's a triangle, but it's tilted. So that's the region that we're talking about, the surface, the portion of the plane that we're talking about. And this thing projected down to the xy plane. This is D. So looking down from the top onto the xy plane, we see that this is 2, this is 13. We see this looking down. This is our D. And you have to define this D carefully because those become the integration limits when you go over to the double integral. And this can again be a type 1 or type 2. There's no major difference for this problem right here. Let's just do a type 1. Let x go from 0 to 13. And y is going to go from 0 to, what's this thing? Y is 2 minus 2 over 13x. Is that right? All right, so that's our D. You have to get D right because D is what you're integrating over. Okay, now the surface area. Double integral over D, 1 plus partial z partial x squared partial z partial y squared under root dA. Once again, the area, the variable bounded by constants has to happen last. 0, 13. Area bounded, the variable bounded by non-constant has to happen first. Then we integrate this stuff. 1 plus partial z partial x. If you solve for z here, z is equal to, I'll write that down, 26 minus 2x minus 13y, right? So partial z partial x is negative 2, and that's a 4. Partial z partial y is negative 13 squared, that is 169. All of that under root dA. Y happens first, x happens last. Okay, so this is radical 174, and oh, that's easy. This is a constant. There's no y, no x in here. Integrate y, you get, that's easy. Easy. So we end up getting 13 radical 174. Okay, so that's the surface area of that triangle. Now you probably could, if you do careful geometry, you probably could figure out the triangle area just by using 1/2 base times height, by doing a bunch of vectors and all that stuff. Probably, but you know, we could also use the formula we derived to calculate that. Okay, that's it for today, and that's it for double integrals for now, and we'll be looking at triple integrals next time.